Electric circuits that contain a number of resistors can often be analyzed by combining individual groups of resistors in series and parallel, as we have seen in earlier sections. However, there are many circuits in which no two resistors are in series or in parallel. To deal with such circuits, it is necessary to employ methods other than the series parallel method. One alternative is to take advantage of Kirchhoff's rules, named after Gustav Kirchhoff, who developed them in the 1800s. There are two rules, the junction rule and the loop rule, and both arise from principles and ideas that we have encountered earlier. The junction rule is an application of the principle of conservation of electric charge to the electric current in a circuit. The loop rule is an application of the principle of conservation of energy to the electric potential that exists at various places in a circuit. We'll start with Kirchhoff's junction rule. Here we show a junction where several wires are connected together. Since electric charge is conserved, and there can be no accumulation of charges at the junction itself, the total charge per second flowing into the junction must equal the total charge per second flowing out of it. In this specific case, the 7 amp current is split into 5 amps and 2 amps at the junction, and 7 amps equals 5 amps plus 2 amps. In other words, the junction rule states that the sum of the magnitudes of the currents directed into a junction equals the sum of the magnitudes of the currents directed out of the junction. Again, this is due to the conservation of charge. An intuitive way to think about this is with water in a circuit of pipes. The electrical current is analogous to water flow, and a junction in a pipe is like a wire junction in an electric circuit. We know that, since the amount of water is conserved in a closed pipe circuit, that the total rate at which water flows into a junction must equal the total rate at which it flows out of the junction. To help explain Kirchhoff's loop rule, let's examine a circuit in which a 12-volt battery is connected to a series combination of a 5 ohm and a 1 ohm resistor. The current flows from the positive or higher potential terminal of the battery around the circuit and back to the negative or lower potential terminal of the battery. The blue plus and minus signs associated with each resistor remind us that, outside a battery, conventional current is directed from a higher toward a lower potential. Using Ohm's law, V equals IR, as the current moves left to right through the 5 ohm resistor, there is a potential drop of 10 volts across the 5 ohm resistor. Similarly, there's another drop of 2 volts across the 1 ohm resistor. Keeping in mind that the potential is the electric potential energy per unit charge, let us follow a positive test charge clockwise around the circuit. Starting at the negative terminal of the battery, we see that the test charge gains potential energy because of the 12-volt rise in the potential due to the battery. The test charge then loses potential energy because of the 10-volt and 2-volt drops in potential across the resistors, ultimately arriving back at the negative terminal. In traversing the closed circuit loop, the test charge is like a skier gaining gravitational potential energy and going up a hill on a chairlift, and then losing it to friction and coming down and stopping. When the skier returns to the starting point, the gain equals the loss, so there is no net change in potential energy. Similarly, when the test charge arrives back at its starting point, there is no net change in electric potential energy, the gains matching the losses. The loop rule expresses this example of energy conservation in terms of the electric potential and states that, around any closed loop, the sum of the potential drops equals the sum of the potential rises. In this specific case, the sum of the losses, 10 volts plus 2 volts, equals the sum of the rises, or 12 volts. Kirchhoff's loop rule can be applied to any circuit, even when the resistors are not in series or in parallel. The two rules are summarized as follows. The junction rule states that the sum of the magnitudes of the currents directed into a junction equals the sum of the magnitudes of the currents directed out of the junction. The loop rule states that, in any closed circuit loop, the sum of the potential drops equals the sum of the potential rises. An equivalent way to express this is to say that the sum total of all the rises and drops around a closed circuit loop is equal to 0. To illustrate the utility of Kirchhoff's rules, let's examine this multi-loop circuit with 3 resistors and 3 batteries. The currents are unknown, but labeled, and we see that none of the resistors have the same current running through them. This means that no resistors are wired in series, and we cannot simplify the circuit by combining resistors in series. Also, none of the resistors have the same voltage across them, so no resistors are wired in parallel, and we cannot simplify anything. We therefore need to apply Kirchhoff's rules. We start by identifying the loops. There are 3, one on the left, one on the right, and one around the outside. Next, there are 2 junctions, one at B and one at C. Finally, there are 3 branches in the circuit, each already labeled with a current. Note, when you set up your own problems and label the currents, the directions you choose are arbitrary. In the end, you might get a negative value for one of the currents, and that will mean your initial direction choice was opposite to the actual direction. Note also that in this circuit, there are 2 junctions, but we will only use one for the junction rule. The second one only gives redundant information. In general, if there are n junctions, then you will use n-1 of them when applying the junction rule. The same goes for the loops. In our case, we identified 3, but will only use 2. In general, if there are n loops, you will use n-1 of them when applying the loop rule. Once the currents have been labeled in the circuit, it's helpful to mark the ends of the resistors with plus and minus signs as shown. The signs indicate the high and low potential sides of the resistor and are placed as such since the current flows from a higher to a lower potential. The signs will make it easier to apply the loop rule. First, however, let's apply the junction rule at B. We find that I1 plus I3 equals I2. Now, let's apply the loop rule around the loop ABCDA. The sum of the rises and drops around the loop must total 0. Starting at A and going towards B, there is a potential drop across the resistor R1. How do we know it's a drop? That's because of the way we labeled the plus and minus signs on the resistor. We moved from plus to minus, so it's a drop of magnitude I1 R1 and gets a minus sign in our sum because it's a drop. Next, in moving from B to C, we encounter a battery. Note the plus and minus signs labeled on the battery. We are moving from minus to plus, so we get a potential rise of 7.0 volts, and the term gets a plus sign in our sum. Next, we encounter resistor R3 and go from minus to plus. The magnitude of the change in potential is I3 R3 and has a plus sign since it is a rise. Next, going from C to D, we encounter another battery. We go from minus to plus, and traversing the battery gives a rise of plus 3.0 volts in our sum. Finally, we set this entire sum equal to 0 in accordance with the loop rule, which, again, is a statement of the conservation of energy. We can do the same thing for the second loop, BEFCB, to get negative I2R2 plus 5.0 volts minus I3R3 minus 7.0 volts equals 0. Note that we could have also used the loop AEFDA, but can only utilize 2 loops in this case. We have 3 equations, one from the junction rule and 2 from the loop rule. Now suppose that we were given the values of the resistors as shown. Our 3 equations then reduce to the following. Note that we are not explicitly writing the units on the resistors in order to reduce the clutter. We now have 3 equations and 3 unknowns, the currents. We can find the values of the currents by applying the methods used to solve simultaneous equations. We'll leave this for you to work out. There is a review for solving simultaneous equations in Appendix C of the textbook. The answers are I1 equals 1.7 amps, I2 equals 0.72 amps, and I3 equals negative 0.98 amps. The general strategy in applying Kirchhoff's rules to multi-loop problems is as follows. First, draw the current in each branch of the circuit, as we have done in this example. The directions are arbitrary. If your choice is incorrect, the value obtained for the current will turn out to be a negative number. Next, mark each resistor with a plus sign at one end and a minus sign at the other end in a way that is consistent with your choice for the current directions in step 1. Outside a battery, conventional current is always directed from a higher potential, the end marked with a plus, toward a lower potential, the end marked with a minus sign. Next, apply the junction rule and the loop rule to each loop, obtaining in the process as many independent equations as there are unknown variables. In this case, we had obtained 3 equations and 3 unknowns. Finally, solve the equations obtained in step 3 simultaneously for the unknown variables. Again, a review for solving simultaneous equations is given in Appendix C of the textbook. We summarize by reiterating Kirchhoff's rules. The junction rule states that the sum of the magnitudes of the currents directed into a junction equals the sum of the magnitudes of the currents directed out of the junction. This is reflected by the law of conservation of charge. The loop rule states that, around any closed circuit loop, the sum of the potential drops equals the sum of the potential rises. Another way to express this is that the sum total of all the rises and drops around a loop is equal to 0. The loop rule is a manifestation of the conservation of energy.